All right, I want to solve another system. Again, I don't know why I didn't erase that because I don't care what it tells me to do. I'm going to Gaussian elimination. I'm going to use Gauss-Jordan because I'm going to put it into reduced row echelon form. Whatever, solve it. Boom, just solve it. Just solve it. I don't even care what example it is. It's an example. Whatever. Just solve it, okay? And that's what we're going to do. And I'm going to use the method of matrices, and I'm going to use the method of converting it into reduced row echelon form, and I'm going to use my calculator. That's the method that I'm choosing for this example. Obviously, there are multiple methods, but this is the method I'm choosing for this one. I need to, of course, write my augmented matrix for this system, which is this, right? My X column, Y column, Z column, equal, and then constant. It's already in the form that I want it to be in, so that's lovely. This is another 3x4 matrix. And so I'm going to use my calculator. I'm going to put it into matrix C, just to pick another one. So over here, matrix. So second, and then this button to pull up matrix. You can see I have a matrix in A and a matrix in B. So you have to remember where you put your matrix. I'm going to put this one in C. So over to edit, and then I'm going to go down to C just to show you that you can input multiple matrices if you need to. Enter, just remember where you put it. And I want to say that matrix C is a 3x4 matrix. It has 3 rows and 4 columns, right? Going across row 1, I have 3, -4, 4, and 7. So 3, enter, -4, enter, 4, enter, and 7. Again, I'll check my matrix at the end just in case. Anyway, row 2, 1, -1, -2, 2, 1, enter, -1, enter. I forgot what I said. -2, 2, -2, 2. Row 3, going across, 2, -3, 6, 5. 2, enter, -3, enter, 6, enter, and 5. And then I'm going to double check and make sure I input it correctly. So I could, glance here. I could glance here. Across the top, looking good. Across the middle, looking good. Across the bottom, looking good. So I input it properly. Now, I want to do stuff with this matrix. My matrix is in, and it's in matrix C. Now I want to do stuff with it. I want reduced row echelon form. So let's go back to our home screen, second mode, so that I quit, just to get a nice clean home screen. Back to matrix here. So I have to press second, and then this button. Don't forget matrix C, but I want to actually do math first because I want to tell it down, down, down. RREF, reduced row echelon form, enter. 4, pull up my matrix, back to matrix again. Matrix C. Close parentheses. Reduced row echelon, a form of matrix C. Boom. There it is. Now this is an interesting matrix that came out of that. Let me write that down. I have my reduced row echelon form. I have across the top 1, 0, -12, 1, 0, 1, -10, -1, 0, 0, 0, 0. So this is a bit different than my last example. My last example had zeros here and a 1 here. This is different. It doesn't look like reduced row echelon form either because I'm supposed to have 1s down the diagonal, 0s in the lower triangle, and 0s in the upper triangle. So something's going on with this system. Let's see. Let's analyze this. Now, if I were to rewrite this back into system of equations, going across the top, I have 1x plus 0y minus 12z equals 1. And I have 0x plus 1y minus 10z is equal to -1. And then if I write this one, it's 0x plus 0y plus 0z is 0. I have 0 equal to 0. If I go and I write this. What the heck? So this one versus this one, this was a false statement. This one is a true statement. So what kind of system do I have? This has infinite solutions. Now I'm not done though. I'm not done with this. I do realize that it has infinite solutions. So when these three planes intersect, they're intersecting at a line. And when three planes intersect at a line, I have infinite numbers on a line, so there are infinite points that work for all three equations. But there's a way to represent an infinite solution case. And again, it's preference. So what do I mean by that? Let me copy this down and show you what I mean. Now, you guys, that's not what I wanted to do. Your book, everybody's book is different. Everybody personally is different. How you represent an infinite solution case. I like to represent my infinite solution case as an ordered triple in terms of x. Sometimes you want to be in terms of y, sometimes in terms of z. I like mine in terms of x. If you're using my math lab, it might ask you for a different situation. It doesn't matter. It's all the same thing anyway. I like mine in terms of x. My system, my ordered triple, I want everything in terms of x. That means my x coordinate in terms of x, which is x, my y coordinate in terms of x, and my z coordinate in terms of x. So once you have infinite solutions, then how do you represent your answer? Your book might ask for it in terms of z. I guess I could show you that also after, but I want to start with in terms of x because I think that one's the best. And I'll show you why at the end. So let me go on, say this is equation 1, and equation 2, and equation 3. Let me go to equation 1. X minus 12z is equal to 1. This is very easy to manipulate and get z in terms of x. Because all I have to do is isolate z. So subtract x from both sides. Right? 1 minus x. And then divide both sides by negative 12. Z is equal to 1 minus x divided by negative 12, which you don't leave a negative on the bottom of a fraction. You technically either put it in the front or put it in the numerator. But if I put it in the numerator, it's going to change the signs of each of these terms and make this a positive x and a negative 1 and change that sign on the bottom. So yeah, if you need more detail about that, I'll show you in a second. But this, we don't leave negatives in the bottom of a fraction. We bring it to the front or bring it to the top. And bringing it to the numerator will clean it up a little bit better because it's going to change all those signs and have a nice leading standard form. So I have z in terms of x. Z is x minus 1 over 12. Now I just need y in terms of x. So equation 2 has y and z, but I need x. So what I'm going to do is replace z with this expression of x so that I can get y in terms of z. So you got algebra going on here. You know, this is very important because now I need to solve for y, which is actually not that bad to isolate y. I just got to simplify this thing. So, all right, so first of all, 10 over 1, right? 10 is divisible by 2, and 12 is divisible by 2. So let me do that. 10 divided by 2 is 5. 12 divided by 2 is 6. Okay, so I'm kind of simplifying the fraction that's going to come from there. I'm going to do more. So a couple things you could do. You could distribute if you want the 5. What I'm going to do is take this whole term and move it over here. So I'm going to add it, this whole thing, so that it cancels on this side and goes over here. So y is negative 1 plus this whole thing, 5 times x minus 1 over 6. You can leave it like this, but I might put it as a single fraction, which means I need a common denominator. So negative 6 over 6, which would be negative 1, plus this 5 times x minus 1 over 6. So I'm just going to do a little algebra to pull them together. I'll show all my work. Negative 6 plus, I'm going to distribute this 5 also. 5x minus 5 all over 6. And then I have like terms in the numerator. So 5x minus 11 all over 6 is my y in terms of x. 5x minus 11 all over 6. This is my infinite solution case. This is my ordered triple that represents any point in the world that satisfies that system of equations which has infinite solutions. Why do I like it in terms of x? Because, you know, once I pick a value of x, let's say x is 0, I get an ordered triple. When x is 0, y is negative 11/6, and z is negative 1/12. When I want another point, you know, plug in 1 for x, 1, and then plug in 1 here, and then simplify, plug in 1 here. So you can get any point in the world that would satisfy just really quick by choosing different values of x, because there's infinite solutions that work, infinite points, infinite ordered triples, because it's a system of 3 variables. So again, it all depends. Sometimes you're asked to do it in terms of x, sometimes in terms of y. So what does that mean when you're told in terms of? In terms of x means all x stuff. In terms of y means all y stuff. So then this would be y. In terms of z would be all z stuff, and then that would make this z, and then expressions here of z. So it just depends what you want. And, you know, obviously it all requires algebra to do what you need it to do.